Hello, AP Physics students. Are you ready for another problem with Mr. Kirsten? All right. So we're going to look at problem number 37 from chapter 4. And this is also going to serve as a little bit of a lecture on friction. This is the first of our forces that kind of take us out of the ideal world. So I think that's kind of cool. So I'm going to kind of split up things a little bit here. Over here, I'm going to talk about friction in general. And over here, I am going to talk about problem 37. So kind of two things going on tonight. What we'll do is we'll kind of use start out on the problem, and then when we need to, go talk about friction. So let's read the problem here. It says a 48 Newton force is required to start a 5 kilogram box moving across a horizontal concrete floor. What is the coefficient of static friction? If the 48 Newton force continues, the box accelerates. What's the coefficient of kinetic friction? I'm sorry, I said static friction before. Okay, well, first of all, let's figure out what in the heck we mean by a coefficient of static or kinetic friction. So mu sub k or mu sub s is the coefficient of kinetic friction so mu sub k is the ratio between the force of kinetic friction and the normal force, whereas mu sub s is the force of static friction to the normal force. Now, what is a kinetic friction force? What is a static friction force? To demonstrate this, we're going to bring in a guest speaker today, Roy Griak, longtime cross-country coach. So Roy here is going to demonstrate static friction. Whenever you push on an object and it is not moving, there is static friction. Think of static, not moving. So even though I'm applying a force to Roy here and he's not moving, that's because there's a static friction force going in the opposite direction of the applied force. Now, when an object is moving and there's still a friction force, that's kinetic friction. All right. So kinetic friction force is moving friction. Static friction is not moving. Thank you, Roy. Thank you. Okay. So notice that mu, the Greek letter mu, is dimensionless. That is, its units would be newtons per newtons, and newtons would cancel out. So mu has no label to it. It's simply a ratio. Okay, so this is what we're trying to solve for in this problem, a coefficient of kinetic friction or a coefficient of static friction. Now, the larger mu is, the more friction you have. And just to give you an idea of some different mu's that are common, you can open your book to the section on friction and kind of get a look at some typical mu values here. For instance, well, that's probably hard to see, but the largest mu is about 1. That's rubber on solid surfaces. And the smallest mu we have in our table here would be Teflon on Teflon, 0.04. So, again, the larger mu is, the more friction there is. Okay, let's go back to our problem then, now that we know what in the world we're looking for. So basically, we are looking for mu sub s in part A and mu sub k in part B. Okay, so let's start with what we know here. Let's do a free body diagram. It looks like we have an object. It's a box, okay? And the box is sitting on a surface, and it looks like we know that the mass is 5 kilograms. It looks like it's moving on a horizontal floor, and it looks like there's some force F that's being applied to it, and F is 48.0 newtons. All right. Okay. We also would know here, let's draw in other things that we would know. There would also be a weight, right? So let's label that in there. And as we know by now, well, W would be mg, or 5.0 times 9.8, or 49 newtons. All right. And there would also be a normal force. We recall that the normal force is the upward force that a surface exerts. In this situation, we know that the acceleration in the y direction is 0. That is, this box is neither accelerating upwards nor downward. Therefore, the net force in the y direction must be 0. Therefore, in magnitude, the normal force must equal the weight. Okay, so the force of the weight down is counteracted by the normal up. Then we have friction. Your book labels friction with a F sub FR. All right, and that's what kind of we're looking for, because we know if we know friction, then we could figure out what say the static friction coefficient is. All right. Well, in this problem, since the box just starts to move when you apply a force of 48 newtons, basically what we're assuming there is that the force of static friction in magnitude is just equal to the applied force. When that force gets just equal to, or maybe just a hair bigger than the friction force, that's when movement starts to happen. We know that the friction force is equal to the coefficient of static friction times the normal force, right? And that would be equal to this applied force. Therefore, the coefficient of static friction would have to be F divided by N. And plugging that in, we would get 48 newtons divided by 49 newtons, and we would get mu sub S equal to 0.98. Okay, so the coefficient of static friction here is 0.98, and notice there are no units here. Okay, before we move on to, this was part A, before we move on to part B, let's talk a little more about friction here. So as we said, friction, let's see, say the force of static friction is proportional to the normal force, okay? Why is friction proportional to the normal force? Well, let's find out. Everyone, we're going to do a demonstration. Put your pen down, okay? Take your hands, put them together, and lightly press them together and rub them back and forth. Not much going on, okay? Now, push them together harder and rub them back and forth. Oh, my hands are burning, they're hot, there's so much friction. In other words, when I push the hands together harder, that is made more of a normal force, there was much more friction force, right? Think of a car in the winter that's sliding around. Sometimes we put sandbags in the back of our cars or trucks to try to get more normal force over the tires that are moving to get more static friction. Friction is proportional to the normal force. What else do we know about friction? Friction acts parallel to the surfaces. So we've got some equations for friction. We know friction is proportional to the normal force. It depends on the nature of the surfaces, or mu. We know that friction acts parallel to surfaces, and it always acts in a direction parallel to the surface and opposite the direction of motion or attempted motion. Okay, so that is some more information about friction. why don't we apply that to part B of this problem? In part B of this problem, it says that the box starts to move. And of course, as soon as the box starts to move, we're no longer dealing with static friction. We would then be dealing with kinetic friction. Kinetic comes from the Greek word kinos, which means movement. So kinetic, moving, static, not moving. Okay, so as soon as the box starts to move, it accelerates, and the acceleration, we're told in the problem, is equal to 0.7 meters per second squared. Okay, so we know that we have an acceleration of 0.70 meters per second squared. Okay, well, let's apply Newton's second law here. We know that the acceleration should be equal to the net force divided by the mass, okay? Acceleration's net force divided by mass by Newton's second law. Well, what is the net force? Well, we know that the normal and the weight are going to cancel each other. Therefore, this applied friction force, which we're applying to the right, which we're kind of assuming is the positive direction, okay, is equal to F minus our force of friction. Again, I'm going minus here because this would be the negative x direction divided by the mass. Okay, well, let's see if we can't solve for the coefficient of kinetic friction here. If we rearrange things here, we get AM is equal to F minus mu sub k times the normal force. So I'm using, for our friction, we're using the mu times the normal force, in this case the coefficient of kinetic friction. And that's what we want to solve for. So if we take this a step further, plugging in for the normal, which is equal in magnitude to the weight. So we've got mg here for the normal force here. Notice that both the weight and the normal force are equal to each other. Now, we're going to have to do a little bit of algebra here. But if we do, I think we know everything in this equation with the exception of mu k. So if I go mu k mg, move that to the other side, that's going to be equal to F minus am. And if we bring this all up here, I am going to get mu sub k is going to be equal to F minus am divided by mg. All right, and then if we plug in a whole bunch of numbers here, we are going to get 48 minus 0.7 times 5 divided by 5 times 9.8. And if we plug that all into our calculator, we are going to get a mu k equal to 0.91. All right. So kind of some tricky equations there, kind of some tricky free body diagrams, some new information about friction, and nice work, physicists, on solving this pretty difficult problem. And we have a special reward for you here for all of the hard work. I have my Norseman, that's Olson Middle School, 1988 yearbook here. Let's take a look here at Mr. Kirsten's 7th grade picture. And there is Mr. Kirsten. Oh, right there. Oh, look at that good-looking guy. Oh, all right. It's kind of hard to see that, isn't it? All right. Nice job, physicists. If you have questions about friction or this problem, make sure you ask. And good work. All right. Take care.